Existing vision language models are designed for image-level tasks such as classification and retrieval. In this paper, we aim to enhance the image-text pre-training for region-level downstream task, which is open vocabulary detection. At pre-training, we propose to randomly crop and resize regions of positional embeddings instead of using the whole image positional embeddings. This better matches the use of positional embeddings at region level in the detection fine-tuning. In addition, we replace the common softmax cross-entropy loss in contrastive learning with focal loss to better learn the informative yet difficult examples. We achieve state-of-the-art on LV's open vocabulary detection, outperforming the best existing method by a large margin. Surprisingly, ROVID improves the image-level representation as well and achieved the state-of-the-art on image text retrieval benchmarks. As mentioned in the previous slides, our motivation is to enable vision language models to help open vocabulary detection task. The open vocabulary detection is where a detector is trained with base categories, but at inference, it needs to detect unseen novel category objects. Previous OVD methods have been using pre-trained clip models and focus on knowledge distillation or pseudo-labeling using the pre-trained clip. One representative work is VILD. It trains a new detector, and the detected ROI line embeddings are matched with the text embeddings of base categories, which are pre-computed by the pre-trained clip text encoder. At the same time, each ROI features are enforced to be close to the image embeddings of the region crops, which are computed by the pre-trained image encoder. This is to preserve the knowledge of the clip pre-training so that the region embeddings can be generalized to unseen novel vocabularies at test time. In this paper, we propose a simple pre-training fine-tuning framework for open vocabulary detection without the need for knowledge distillation or pseudo-labeling. Instead of training a new detector from scratch as in the previous works, we initialize the detector with a VID backbone that's pre-trained by contrastive image text pre-training. Only the detector heads are newly added. The way ROI features are used in region text embedding matching is the same. At test time, the novel category embeddings are introduced and the detected regions are matched with both base and novel category embeddings, and their region text similarity is treated as their detection scores. We mainly experiment on the LV's OVD benchmark, where the base categories are the frequent and common splits, and the novel categories are the rare categories. Mask AP on rare categories or AP rare is the main metric here. We observe our baseline with VID base backbone performs reasonably well, which is only slightly behind the previous VILD method based on the VID large backbone. As our method directly initializes with the pre-trained VID and fine-tune the detector from there, we observe there is a gap between the image-level clip pre-training and OVD fine-tuning. At pre-training, we typically use image size 224, which results in 14 by 14 image tokens. Then these are added with the positional embeddings of the same shape. There are following transformer blocks and a global average pooling at the last layer, where we obtain the image embedding, which is then matched with the text embedding. On the right hand side shows the OVD fine-tuning, and typically higher resolution images are used for detection. For example, with image size 1024, we have 64 by 64 tokens. As we have smaller number of positional embeddings pre-trained, the positional embeddings are commonly bilinearly upsampled to fit the resolution. After the VID backbone are the added detector heads, and each region embeddings are matched with text embeddings. When we look at the last layer where the region crop happens on the feature map, we can observe the positional embedding information is also being cropped, and so each region embeddings will contain only the partial positional embedding information. However, this is different to the pre-training because the VID encoder in pre-training has always seen the full image positional embedding instead of the cropped one. To bridge this gap, we propose cropped positional embedding or CPE in our pre-training. For each image, we upsample the positional embeddings into a larger size and randomly crop and resize a region into the original 14 by 14 shape PE. Intuitively, learning with CPE allows the model to view an image not as a full image in itself, but as a region crop from some larger unknown image. And this better aligns with the use of positional embeddings in downstream OVD tasks. We observed that pre-training with CPE improves the baseline by 2.4 AP rare. In addition, we propose to use focal loss in the clip pre-training. This allows us to have finer control over hard examples and helps focusing on the novel concepts. We observe focal contrastive loss provides further improvements. In OVD fine-tuning, we observe that many novel objects are often missed in the proposal stage because they tend to be classified as background. Inspired by the OLN work, we replaced the binary classifier in RPN with centeredness prediction layer and treat the centeredness as the objectiveness score in detection. We observe further boosts, and when combining all our ROVID improvements, we achieve a large gain of 5.8 AP rare over the baseline. As our OVD detector depends on the pre-trained backbone, it's important to set the backbone learning rate lower than the rest of the detector heads to prevent forgetting in the fine-tuning process. We evaluate the learning rate ratio between the backbone and the detector heads. We found 0.1 to be the sweet spot. We also study whether the benefits of our improvements scale well with the backbone capacity and contrastive batch size. We observe consistent gain of our ROVID methods in all settings. In comparison with state-of-the-art methods, our ROVID outperforms best fit-based method, OLVID, and CNN-based Wild ensemble by large margins. Surprisingly, ROVID performs very well on image text retrieval tasks, outperforming all published works. This shows that our pre-training method not only improves the region-level representation, but also global image-level representation for retrieval. In conclusion, we propose a simple image text pre-training framework to bridge the gap between image-level pre-training and open vocabulary detection fine-tuning. Our proposed CPE and focal loss introduce no extra parameters and minimal computations. We hope this can help the research on open vocabulary detection from the perspective of image text pre-training, which can benefit both image level and image level tasks. Thank you.